Okay, so then let's start today's research seminar. I'm very happy to introduce Mr. Weihua from Stanford University. And I want to briefly introduce today's speaker. Weihua Hu is currently a PhD student of computer science at Stanford University, advised by Yuri Reskovec. And so his main topic is for graph learning, representation learning, and its application to scientific discovery. Actually, he is one of the co-author of a very well-known graph neural networks method called graph isomorphism networks called GENE. So I think this is very well-known method in the community. Also, he did very nice work for the other research related to graph neural networks like pre-training and including today's topics. So, okay, so anyway, he's a very rising star in the community. So please enjoy his talk. And so Weihua, please start.
Yeah, okay, sounds good. Thank you. Thank you for the introduction and thanks for inviting. So I'm Weihua and today I'm excited to talk about my work, Open Graph Benchmark Large Scale Challenge. It's a joint work with my amazing collaborator, Matthias, Hongyu, Maho, Yushao, and Yuri. So I'd like to start by saying that graphs are everywhere. Many real-world objects can be naturally represented as graphs, like molecular graphs, social networks, knowledge graph, biological networks, citation networks, 3D meshes, abstract syntax tree, and so on. And once these are represented as graphs, they are basically graphs are just a set of nodes and edges, and we can use kind of unified machine learning models to make prediction over them. So we are interested in machine learning problem over this graph, like predicting the property of molecules, which will be the prediction over the entire graph. We're interested in predicting new friendship in social network, which will be a link prediction. And we're interested in, for example, predicting the functionality of the protein function interaction network, which will be a node classification problem. And the graph representation learning is a very promising paradigm for graph machine learning. It aims to map nodes and graphs to an embedding space such that the similar nodes or similar graphs are mapped into similar vectors. And using these vectors, we can perform machine learning tasks like graph classification, link prediction, node classification. So graph machine learning is very hot topic in machine learning. Interest in graph machine learning is increasing. For example, if you look at the last several years, the ICLR conference, the most growing keyword is the graph neural network. So the question, so a lot of paper has been published. And the question we ask here in our work is, how can we further advance the field of machine learning research on graphs? So historically, we've seen that the benchmark datasets have played a very important role. For example, in computer vision, ImageNet and MS Coco are very popular. We have this ImageNet moment that made this convolution network very successful. In NLP, we have a squad and glue benchmark that again kind of catalyzed the research progress. However, if we look at the graph machine learning, there are a lot of issues with existing graph benchmark. For example, the issues are like the data sets are very small, too small to be realistic. Evaluation protocol is often not unified, and dataset splits follow conventional random splits, while when we deploy these models to real world, we'll encounter distribution shift. And as a result of all these issues, it's very hard to rigorously evaluate graph machine learning models. And it's hard to make progress for the field. So in May 2020, we introduced Open Graph Benchmark, in short OGB, which is a realistic and diverse benchmark datasets for machine learning on graphs. And OGB is available in this website, ogb.stanford.edu. We have a paper published at NeurIPS, and we have GitHub repository that contains all the code to provide the data sets and all the baseline codes we have. So OGB includes 15 data sets from diverse domains and tasks. These 15 datasets are here. So we have we cover 3 core graph machine learning tasks, like prediction at the level of nodes, prediction at the level of links, and prediction at the level of the entire graph. We have graphs with different sizes, ranging from small, medium to large, and the graphs from different domains, like those graphs from biology or chemistry from nature domain, as well as graphs from social networks and the information network. So we prepare this collection of data sets for machine learning community to explore. So it's been like about 1 year since we introduced this OGB, and the many methods have been developed on the OGB. So over 300 leaderboard submissions have been made on our data sets, and the drastic accuracy improvement on many data sets have been observed. For example, this MoPCABA is a molecule classification data set, and like our baseline is like this, and there's a huge accuracy improvement recently, as you can see here, where x-axis is the date and y-axis is accuracy. We observe similar trends for other data sets. Here's the product classification data set, where we again see the sharp increase in accuracy driven by the methodological innovation. However, these innovations are great. However, if we look at the deep learning breakthrough, this breakthrough has been driven by training big expressive model on large data, like deep convolution network trained on ImageNet, or large transformer network trained on large text data. And OGB is a larger than existing benchmark, but they are still very, very small compared to this ImageNet or text data that's generated huge success in computer vision and NLP. So we think there's a need for large-scale benchmark that's comparable to ImageNet or this large-scale unlabeled data in this computer vision or NLP. And also we want to emphasize that machine learning on large-scale graphs is very challenging problem and requires innovation. For example, training this graph neural networks on large graphs is very hard and requires non-trivial mini-batch sampling of nodes and edges. So machine learning on large graph is not just about using more GPU, more CPU, but it's also about innovating new method to training this state-of-the-art model on large graphs. And so for this KDD Cup 2021, we introduced a set of 3 challenging, very large-scale graph data sets that I'm going to introduce later. So the web page is under this ogb.stanford.edu. We have paper describing this challenge, and the GitHub repository is also here, so you can feel free to access it. So this OGB large-scale challenge, OGB-LSC, was in the KDD Cup, which we just held the workshop 2 weeks ago. It attracted huge attention from the community. We got 500 team registrations across the globe. We have 143 teams submitted to the initial test submission, 123 teams submitted to the final test submission, and we give up 3 winners, 3 awards per data set. So there are 9 winners in total. There are 3 data sets, so there are 9 winners in total. And we have this kind of a country distribution, mostly from China. We also have participants from US, Asia, Europe, and other countries. And in terms of institution, they're kind of balanced, a bit more in academia. And the registration per data sets is like this. So we prepared the node classification, link prediction, graph classification data sets, and we attracted a lot of team registration for this data set. And the big kind of characteristics of this large scale challenge is that our graph data sets are really orders of magnitude larger than existing data sets. For example, this node level data set is has a 244 million nodes, which is like 100 times larger than OGB's comparable data set. And we have this knowledge graph data set that's again super large. We have this molecule data set that's again unprecedentedly large. And we think, providing this data sets to the community would allow some kind of breakthrough similar to like ImageNet and the NLP breakthrough. And we also ensure each data set is practically relevant. So let me know if there's any question so far.
So I have one question. So how did you find this data set?
Yeah, I'm going to introduce this later. Yeah, thanks. So now what I'm going to do is to talk about each data set, talk about how we collected these data sets, where these data sets come from. We talk about our benchmark analysis on these data sets, and we also talk about how the winners of the KDD Cup perform and any lessons that we've learned from the KDD Cup, so that to provide some directions for the community to explore. Let me first talk about this node level track, node classification data sets. So here, our task is to predict the primary subject area of archive papers in heterogeneous academic graph. So we have this academic graph. We have three kinds of node types: paper nodes, author nodes, and institution nodes. Paper nodes cite each other, so we have these citation links. Author nodes, some authors, write papers, so we have this rights relation. And authors are affiliated with some institutions, so we have this affiliated with graph. And our goal is to predict some category of this paper, the archive category of this paper. And this motivation is really the volume of scientific publication is increasing exponentially. And these labels are often manually annotated. So we want to, reduce the burden of manual labeling. And we also want to use this classifier to classify all the papers in this citation, in this academic graph, including non-archive papers. So that's motivation. And this data is extracted. We extracted 121 million academic papers in English from something called Microsoft Academic Graph, which is open source. And we have 122 million authors and 26 institution nodes. And in terms of data split, we want the users to train models on papers published until 2018, validate the performance based on papers in 2010, 2019, and test the model performance on papers in 2020. So this kind of simulates the realistic scenario where we need to make prediction on the paper that's newly published. And it's a very massive graph. We have 240 million nodes in total. It's 1.7 billion edges across the edge types, and this kind of requires efficient sampling strategies to train state-of-the-art graph neural networks. So the total the statistics are summarized in this figure. And yeah, and the challenges in this graph is also we have rich feature representation for nodes. We extracted this 700 dimensional feature vector obtained by Roberta sentence encoder, and in total our data set is 180 gigabytes storage, and requires the efficient IO strategy. Even in terms of machine learning system perspective, so requires this efficient IO strategy to handle this graph. And for the benchmarking models, we consider several baseline models, including just applying multi-layer perceptron to predict the paper category, some label propagation method, and also some GNN method, simplified graph convolution and others, and GNN models, including graph stage and graph attention networks. also like our graph is heterogeneous, containing paper nodes and institution nodes, author nodes. We also consider the relational GNN model that exploit this heterogeneous property of the graph. And that's called a relational graph stage and relational graph attention network. And this NS means neighbor sampling. So in order to train GNN large graph, we need sampling of the neighborhood nodes. And what we observed in our initial benchmark analysis is that GNN outperform more simple models. Like these are like outperforming these models, and heterogeneous information is really crucial. And this is very interesting because recently, like in GraphML community, people are kind of trying to make the models simpler and simpler in order to scale models on large graph. But historically, we know that on larger and larger data, we need more and more expressive models. And this baseline analysis kind of shows that we do need some expressive models to capture the complex, complex relation large data, although it's hard to implement. And the winners are like this. We have winners from Baidu, DeepMind, and the Scenarize AI group. And these are the performance numbers. And if you look this pictorially, it's very impressive. Our best baseline. So what x-axis is the rank in the final test submission. Y-axis is the accuracy, and we see that the winners really outperform our best baseline, which is their state-of-the-art, graph attention network by a large margin, like about a 6% accuracy gain. So we also summarize what kind of techniques are really effective among winner solution, and there are three common trends among winners. The first trend was that all the winners basically use the label information, basically the archive category information, as the inputs to GNN. Like traditionally, GNN basically takes the node features as input and try to predict the node category, the target label. But all these winners start to actually use GNN to propagate the target label, which is very interesting. Also, they develop more sophisticated neighbor sampling strategy to train GNN, which is kind of relation aware neighbor sampling. Also, all the winners exploit this timestamp information of the nodes, because in many real world graphs, we have this temporal information. For example, the publication year of the paper nodes, and the winners kind of exploited this information in a variety of ways, which is very interesting. Other techniques that's used by, for example, DeepMind, which is very promising, is that they use the self-supervised learning objective on unlabeled nodes. So they not only have the supervised laws to predict the category of the papers, like supervised paper, archive papers, but they also introduce some laws, kind of contrastive laws for the papers that are unlabeled, so that GNN can kind of capture some interesting patterns from unlabeled data. So that's the kind of a summary for node level track.
I have one question. Can I ask a question?
Yes.
So here, the first one's label is used as inputs to GNN. So this means like it's more like semi-supervised learning, or just use the label for the input?
So, sorry, what supervised learning?
The first one is like semi-supervised learning, like label propagation, or using the label information as an input to the GNNs.
Using label information as an input to GNN.
As like one hot?
Yes, as one hot.
But
like what?
So in that case, how do we predict the test samples? Because we don't know the label for the test.
Yes, that's a great question. So the way they did is called masked label prediction, where during training, they mask 50% of the labels and use the rest of the 50% as an input to GNN, and use this 50% for the to train the GNN. So they do not use the labels used for input as the supervised loss. They mask some of the target labels and then try to predict that.
I see. That's interesting. Thanks.
Yes. So in some sense, it's like a learned version of the label propagation, learning to propagate labels and features simultaneously. Yes. Thank you for the question. Okay. Let me move on to the link prediction track. So here, the prediction task is now at the level of links. So we want to predict the existence of link between two nodes. And specifically, we want to predict missing facts and links on massive knowledge graphs. So knowledge graph is a heterogeneous graph. Our heterogeneous graph, we have multiple types of entities and relations. And the facts are in the triple form, in this form called head relation tail. For example, this is a kind of an example of a knowledge graph where, for example, here the head can be the rural, and the relation is located in, and the Paris is a tail. So we have a lot of knowledge about the world can be represented as this head relation tail, and this can be organized into a graph, and that's the knowledge graph. And the challenge with the knowledge graph is that they are heterogeneous. There are so many relationships, and they are incomplete, meaning that there are missing entities and relations, and especially there are a lot of relations that are missing. For example, maybe we don't know this. Maybe for some arts, for some pictures, or we don't know who painted it, and we need to somehow predict those relations. So the data set is called the WikiKG 90 million. It's extracted from the entire Wikidata knowledge base. It's very large. It contains 500 million facts, triples from 87 million real-world entities, and there are about more than 1,000 relations. And I want to emphasize the difference, the existing KG data set. The biggest difference is that we really use the entire Wikidata, and it's much larger than existing KG benchmark datasets. And another difference is that we split this edges based on time. So existing work just to have the entire knowledge graph, and they randomly sample 10% of the edges for testing. But what we did is to consider the newly added edge and try to predict those, which is more realistic. And for our knowledge graph, we provide the text features for entities and relations, while existing benchmarks do not provide those. So in more detail, our data split is based on time. So we download the Wikidata at 3 different timestamps, and we use the edges from September as a training edges. We use this October one for validation, and the November one for testing. And the task is based on the conventional KG completion for each validation test triples, like head relation. We want to predict the tail entities. So, and we basically provide this 1,001 candidate tails, and we want the model to choose one true tail entities out of this candidate tail entities. And the evaluation metric is commonly used, and we use the commonly used evaluation metric called mean reciprocal rank. So the initial benchmark analysis we did was we basically tried the state-of-the-art knowledge graph embedding models. We have 2 phases in knowledge graph embedding models. maps each node, each entity node and relation into the embedding space. And decoder will basically score the triples head relation tail using these embeddings. And we like higher score, the triples with higher score, we assume they're true. They're more likely to be true than those with lower scores. The encoder we use is include the shallow embedding, which is basically just the embedding lookup of the entity and the relations. We also utilize the Roberta embedding, and we have this concat scenario where we combine shallow embedding and the Roberta embedding, concatenating them and somehow merge them in a nice way. And the decoder, we use 4 very widely used state-of-the-art decoder, including transient, dismount, complex, rotate. So these are basically taking the embeddings of the head, relation, and tail, and output the scalar that basically evaluates the likelihood of the triplets. And here's our initial benchmark analysis. And what we observed is that it's very promising to use this Roberta feature and shallow embedding together, and the decoder does not matter much in our scenario. And this is kind of interesting because in knowledge graph embedding literature, people have developed a lot of methods for the model, like a decoder part, but the encoder part might be very promising to explore. And you can see the number of parameters is super huge, like 17 billion parameters. And this is because like we need to learn like specific embedding for each node. And this also creates a very hard like system challenge, like how to train this huge number of parameters efficiently. And the winners of this challenge is are here. The first one is the Baidu team. Second one is the Harbin Institute Technology, and in the third place is a team from China again. And these are the accuracy, mean reciprocal rank. It's upper bounded by 1. So we are very impressed that these teams are able to get near perfect performance on this data set. And this is kind of a illustration of how winners outperform our best baseline. So we see that this huge performance gain, about 10% gain in MR. To summarize this winner solution, what we observe is there are like 3 common trends among the winners. The first one was that winners all use the model ensembling. They ensemble different embedding methods, not just using, for example, transient, but also use the transient and rotate and all these embedding methods together. That seems to improve the performance. And these winners are also kind of try to filter the candidates, the tail candidates, and they find that these candidates with low degrees in the training graph are very unlikely to be the true positive tails. So they kind of measure the statistical frequency of the candidates and try to filter out those candidates that are not promising. And also a lot of methods have been introduced, that kind of for example, smoothing the KG after they train the KG and the knowledge graph embedding of nodes and edges. They provide a method to kind of smoothen the KG embedding that seems to help. And there are a lot of other, like they mine some common rules on KG, logical rules on KG to add some new edges before training KG embeddings. So there are a lot of interesting methods among the winners. By the way, like all these winners' technical reports are available on our website, ogb.stanford.edu. So you can, if you want to know more, you can check that out on our webpage. All the technical reports are there. publicly available, and all the code is also publicly available. And since on this task, like people have already achieved quite impressive performance, like 97% accuracy, and there's almost no room for improvement. The question we ask is this data set solved? And the good news is that it's not really solved, because it's the biggest, like in some sense, problem with the current evaluation is that for each triples, we provide very small number of candidates, nodes, and we only require the winners to rank among those candidates. However, if you consider the real world application, we're never provided this kind of candidates. Like, for example, I want to know like picture A or some film A, who directed this film A. Then I need to basically search over all the 90 million entities to basically answer this question. And we are never given this 1,000 candidate entities. So what we are currently pushing is to push a new, much more challenging version of this data set called version 2, which is constructed based on more recent Wikidata dumps. And very importantly, we do not provide any candidate tails for each validation and test triplets, so that, given a head and relation, the people need to basically search over all the 90 million entities to basically answer the question, answer our task. And 90 million is much larger than this 1,000. And we are currently running some baseline analysis, and we found this number is much lower than it's reported in the KDD cup. So that's what we are planning to do. Yes, so that just kind of concludes the large scale link level track. Any questions?
Just for clarification, is the data only for English, or also includes all the languages?
This is only for English.
Okay.
Yes.
Thanks.
Yes, thanks. Okay, finally, going to move on to the final data set, which is a graph level track. So we want to predict the property of the entire graph. Here the task is to predict a quantum chemical property of molecules. So just to give everyone background, conventional approach to kind of first of all, quantum chemical property is very important to know in this material discovery, drug discovery. And the conventional approach is to use something called DFT, density functional theory, to approximate the Schrödinger equation to compute this quantum chemical property. And the DFT is a really reliable quantum calculation method to approximate or solve the Schrödinger equation. And it's really widely used for drug discovery and material discovery. However, the issue is that DFT is really time consuming. You can see that, in DFT, we start from a 2D molecular graph, and the DFT will take hours for each molecular graph, to just compute this 3D molecular graph. And from there, DFT requires several minutes to compute some quantum chemistry property of molecules. And in practice, we want to compute many the quantum chemistry property of many molecules, and simply applying DFT to those molecules is very intractable computationally. So what's kind of a very promising recently in graph machine learning as application of graph machine learning is to use machine learning model to approximate this very expensive DFT. So this machine learning model will take the 2D molecular graph as input, and then within a time timestamp that's much less than 1 second, it's able to like output this value. For example, homolumo gap energy of the given molecule. And this is much more promising because now we can use this one. We can deploy this to 100 or even 1 billion molecules and without any issue. And we can discover better drugs and materials. So to do this, we introduced this PCQM for medium. It's created under this very super cool project called PubChem QC, developed in Weekend actually, and it contains this 3.8 million DFT calculated molecules from the chemistry database called PubChem. And this is very large data set, and so it takes like a year. It takes a year of compute on very large cluster in Weekend. So it really like costs a lot to produce data set. But once this data set is produced, we have huge opportunity to train machine learning model on this data set so that these much cheaper models can be deployed on even larger molecules that on which DFT has not been performed before. So actually I want to point out the difference to the QM9 dataset, which is also very widely used graph machine learning dataset, quantum chemistry dataset in graph machine learning. The first biggest difference is that this PCQM 4 million is 30 times larger, contains 30 times larger number of molecules. And really this large model, machine learning models really require large number of data. So it kind of opens up this opportunity for breakthrough. Another big difference is that we assume our input is 2D molecular graphs rather than 3D graphs. And this is more challenging and more practically useful because, as I said before, actually the most time consuming one is to compute this 3D molecular graphs based on 2D graph. And our task is kind of take this 2D molecular graph directly as input and try to predict this homolumo gap, while QM9 assume these 3D molecular graphs are given. But this graph itself is very time consuming to compute. So our task is much more meaningful. To say some details about task, we split the data into this ratio, 80-10-10 ratio, and they are split according to the compound ID of the PubChem. Our evaluation metric is simply the mean absolute error. Our target is just a scalar, so we just measure the average of the absolute error on the test molecules. And we also have this interesting constraint on inference budget, because recall that we want our machine learning model to be much faster than the quantum computation, like a DFT. So we constrain our inference budget to be 0.1 second per molecule, and it's 4 orders of magnitude faster than DFT. So it can compute 1,000 or 10,000 times more molecule within the same time. And we did some initial benchmark analysis. Baseline method, we tried 2 different models. The first model is applying NLP over Morgan fingerprint, which is you can think of this as a very state-of-the-art thing, feature vectors developed by chemistry community to represent the molecules. So it's a feature engineering method. And we also have several state-of-the-art GNN models, including graph convolution networks and graph isomorphism network. And this virtual node is a very recently developed, very promising technique, which is basically adding some, on each molecular graph, we add 1 node that's connected to all the nodes in the molecular graph. And this way, the GNN can capture the global information in each round of message passing. And the GNN there are several observations. The first observation was that GNN models are able to significantly outperform fingerprint model. And here is the mean absolute error. The lower, the better. And you can see these numbers are much lower than this validation performance. And if we consider like a less data, like if we only train the model on 10% of the training data, we observe the performance drop is very huge. So it's kind of justifies the model to be trained on this large data. However, like this number is actually far from what we desire, which is the chemical accuracy, which is the number that chemists will be happy about. And there's a huge like performance gain. So there's still a lot to improve on this task in order to make chemists happy. And another observation that we've seen is that on this task, you see that the model size really play an important role. Deeper and wider model, GNN model, or fingerprint model, MLP perform better. And you can see, we train the GNN with a 5-layer, 3-layer, we make the width either 600 dimensional or 300 dimensional. And we see that, this really, the largest model really outperform other models significantly. Now this is our initial benchmark analysis. What about the winners? And the winners are depicted here. So the first place is from Dalian University and Peking University, Princeton, and the second place is from Baidu. The third place is from DeepMind. And the performance numbers are like summarized here. And just for illustration, this is like a performance improvement that's done during the KDD Cup. By the way, KDD Cup is just 3 months, so it's pretty impressive that the error was decreased by this margin, like probably 0.03. So that's pretty significant. And I want to summarize the 3 common trends that's observed among the winners. First of all, like all the winners use even bigger, meaning deeper and wider models than our baseline models. The second one is that all the winners somehow incorporate the global graph information in each round of a message passing of graph neural networks. And the third one is all the winners try to use the 3D structures of the molecules. Let me elaborate this a little bit. So remember our baseline of GNN layers is like 5 layers, while interestingly, all the winners use this 11-layer up to 50 layers of GNN to achieve their best performance. And the number of parameter is obviously much larger than our baseline. And it's very interesting that, this has never been observed on small OGB dataset, but on OGB large-scale challenge datasets, really people start to realize that larger models can be trained to give impressive performance. The second trend we observed was that global message passing is really, really effective. The GNN message passing, what this means is that, as I described before, in each round of message passing, usually GNN just takes the feature, aggregate the feature of the neighboring nodes. So the input graph is like this, but the winners actually introduce this virtual nodes. Actually, in our baseline experiment, we also do this, but winner either have this virtual node that's connected to all the rest of the nodes in the graph, or they have the transformer style fully connected graph. So they consider the fully connected graph and pass the message to each other to capture the global structure of the graph. And here, they also introduce some encoding, distance encoding, positional encoding, so that the original graph structure is maintained. But basically, they perform fully connected message passing to really let each node understand the property of all the rest of the nodes in the graph. The third very interesting observation is that, like, our task, remember, is to predict some property of the molecule given 2D molecular graphs. But all the winners try to exploit the, because our task has this intermediate 3D structure. So we go from 2D into 3D and then predict the property. In our data set, we only provide the 2D graph and the final scalar value, but all the winners try to model the intermediate 3D structure. And these winners, for example, calculate the 3D structure using more cheaper geometry optimization using some chemistry toolkit. And there are two ways people use this. One is to use this computed 3D structure to supervise models as a training time, using a node embedding to predict the edge distance, or use the 3D structure, their computed 3D structure directly as the input to the model. And of course, this 3D structure is not so accurate, but still helps improve the performance. And so given this, we are going to update the dataset where we provide the DFT calculated 3D graphs only for training molecules. So during training, the people can utilize this 3D graph information. At test time, they still need to make inference based on the 2D graph. But this 3D graph during training might provide useful information. So this concludes my talk. Finally, I'm going to share some future plans of the development of this large-scale challenge. So we're working on the public leaderboards for this, in order for the community to continue to develop new models on these data sets. We are going to update the data sets based on the lessons learned from the KDD Cup. First of all, we're going to split the test set into two things, test dev and test challenge. And we're going to use test dev for the leaderboard and test challenge for the future competition, like maybe next year's KDD Cup or at the other venues, so that people can continue to develop on our data sets and continue to participate on the competition based on our data sets. Also, we're, as I said in our talk, in my talk, we're going to update two data sets. One, this WikiKG into the version 2, where we observe, the original data set, the performance of the winners already achieved 97% MRR, mean absolute error. So we want to make the task more challenging and realistic by not providing any tail candidates. And therefore, for the final one, we're going to update molecule data set into version 2, where we're going to actually fix some error bug in our data sets. And most importantly, we're going to release 3D structures for the training molecule, so that method based on graphs embedded in the 3D structure can be developed. And this has been really popular recently in the research of graph machine learning. So this concludes my talk. Thank you very much.
Yeah, thanks to Weihua for a wonderful talk. It's very, very impressive. From the audience, do you have any questions? So if you have any questions, please directly talk to us or just put your questions to the chat box. Hey, before you guys put in the chat box, I have some questions. So the results is very interesting for, in particular, the deeper neural networks, graph neural networks works, because this is it's a very not commonly known current GNN. But besides the technical contributions, I'm very interested in how did you initiate these projects and how to manage the project. Can you briefly talk about that if possible?
Yes, of course. I'm very happy to share that. So we initiate the project because like we first released this OGB, which was based on this several issues that we realized, existing benchmarks are small and they're not standardized. So we released this OGB last year. And since then, we have seen a lot of kind of developments of the methods. But what we realized is that, first of all, these data sets are still very small compared to a lot of graphs in the industry or scientific applications. So we think, first of all, there's a huge gap to deploy the models developed on original OGB to, for example, Facebook or Twitter or Pinterest or this real world company graph. And that's the first motivation. And the second motivation is that we observed that the models are developed on OGB tend to be rather small and simplified. And we think maybe it's because of our data sets. It's because the scale of our data sets is not large that this, the success, computer vision, NLP success, bigger model, bigger data sets really achieve impressive. Maybe because of our small scale of the data sets that we can't achieve, we don't really see this big model successful. So we just want to test our hypothesis if this is true. And in our initial baseline analysis, we find this to be true. So we kind of implement state-of-the-art methods that are simpler, recently developed simpler model as well as more complex model. And we found this really complex model actually perform better. We start to see this signal. So we deploy this our data sets to the KDD Cup, very well-known competition, to really see if we can push this further, push this direction further, not just doing some simple models, but really scale up this large models. Is there any? And then we do observe huge improvement in scaling up the model. So that's good.
Thanks. Very nice. Yeah. So I also had some impression that so if I really want to solve some particular important problem in scientific discovery, maybe it's good to hold some competition like you built. Like if I have huge data set, maybe it's good to have a competition and then ask the participants to really solve the problems. So what do you think? Is this a good strategy? Like at least from your talk, I had this kind of impression.
Yes. I think like the power of community is super huge. Like if you have this very important problem that everyone cares about, and you show why it matters, and you're able to convince the community, you're really able to achieve crazy performance gain within just 3 months. And this also raises the awareness of your task, so that maybe your data sets will be continued to be used, in the future, even after this competition. So it's definitely good to hold this competition and raise awareness and let the community jump in and involve. Yes.
Thanks. It's very nice. From the audience, do you have any questions? Maybe you present very well, so there's no questions. Okay, so if we do not have any further questions, let's thank the speaker again. So yeah, thanks Weihua for great talk. And so this is the end of talk seminar. And just for advertise, actually we do have another research seminar in every our research seminar in every Tuesday afternoon, mostly, but sometimes we don't have it. Also, if you have a chance, please join the RIKEN YouTube channel. So this talk will be put onto the YouTube channel. Yeah, if you have time, please join it. Okay, thanks. And this is the end of the seminar. Thank you very much.
Thank you very much.
Thanks.